Hello. So this will be our last topic of chapter 1, and next discussion will be we will start with the new chapter, chapter 2, and it's about power. The last topic is about Norton's theorem, and again we will be using this problem just like what we did before from the previous examples, but this time instead of solving for the current that passes through Z2, let's take a look at the current passing through Z1, I1. So that it will differ, the ZTH or the looking back resistance will differ from the first one, the Thevenin theorem. So how do we solve the current passing through Z1 using Norton's theorem? So the concept, the procedures, the first procedure is it's similar with the Thevenin's theorem. We need to solve for the looking back resistance, and it also uses the same concept by removing the voltage sources and replacing them with short circuit or their internal impedance. So first we calculate the Zn, or the looking back resistance or impedance, but our load this time is negative J4, or that's Z1. So if we redraw our circuit, so this will be our new circuit. Just remove the load. Our load will be negative J4. Then replace this with a short circuit. Then we have 3 plus J4. Then a resistor 5. And replace this with a short circuit. And this will be our Zn. It's the same as the ZTH. It's the same method. So if we solve now for Zn, Zn is just equal to the parallel combination of the two. So 5 times 3 plus J4 all over 5 plus 3 plus J4, or that is 8 plus J4. Then this will be, so Zn now will be equal to so 5, that's 15 plus 20i all over 8 plus J4. 2.795 angle 26.57 degrees. Oops. Then after solving that, the next step is to calculate our short circuit current, or the Norton's current. So we bring back our sources, the voltage source. This is 100 plus G10 plus minus. Then we have here the resistor 5 and another voltage source. That is 100 minus G5 volts. So short circuit current, or the Norton's current. So we short this load and we calculate for the current passing through here. And that will be IN. So how do we calculate that current? That current is also this current. And it's actually equal to, if we apply KCL at this point, we have another current here and we have another current here. This current here is just equal to this voltage minus this voltage divided by 5. And the current here is just the voltage here divided by that impedance. But what is the voltage here? It's the same as the voltage here. What's the voltage here? It's also the same as the voltage here, if this is our reference. What's the voltage here? It's just 100 plus J10. So this is also 100 plus J10. So we can do that. So entering negative IN. Then we have the current going here. So that's plus. And that's just equal to the voltage here, which is 100 plus J10. 100 plus J10. All over the impedance, which is 3 plus J4. This is 3 and J4. Then for this current, it should be minus. It's entering. And that current is just equal to the voltage here, which is 100 minus J5. Then we will subtract the voltage here, which is 100 plus J10. So minus 100 minus J10 all over 5. And this should be equal to 0. And we can now solve for IN. We move IN at the other side. Then we add this. And this will be our IN. So we have 100 plus J10 all over 3 plus J4. Then we subtract this one with, so 100 minus 100 will cancel out, minus J5 minus J10, that's negative J15, and it's also negative, so we just add it. So this will be 5 plus 10, 15, J15 all over 5, and equals, and this will be our 18 angle negative 40.95. 18 angle negative 40.95 degrees. This is our short circuit current, or the Norton's current. Then for the Norton's equivalent circuit, so we have, this will be a current source, which is our IN, and it should be in parallel with the impedance ZN, or the looking back impedance, and this will be our load here. So our load is just a negative J4, a capacitor, negative J4, and you want to calculate this current, and this current is I1. And what will be I1? So calculate now. We can just do current divider, because the total current is IN, so just IN multiplied by ZN all over ZN plus the load impedance. So IN, we already know IN, that's 18 angle negative 40.95. Then we have ZN, our ZN is 2.795 angle 26.57. Then we add this with all over plus or minus J4, because that's the impedance of the load. And calculate now for I1. So we have 18 angle negative 40.95. Then we multiply it with the divider. In the numerator, we have 2.795. 795 angle 26.57. And at the denominator, we have 0.795 angle 26.57. Then we subtract J4. And this will be our answer, 13.54. 13.54 with an angle of 33.35. 33.35 degrees amp. So the current that passes through Z1 or negative J4 is 13.54 angle 33.35. So we check from our previous discussion, I1, that's I1. So this is I1, 13.541 angle 33.3491. So it's accurately correct. For the mesh analysis, we have 13.54 and 33.34. So this is how you do Norton's theorem in AC circuit.